Look at this color. You can see it. Your screen can display it. You can point to it and give it a name. Now try to find it in a rainbow. Start at red. Move through orange, yellow, green, blue, and violet. Magenta is not there. There is no single wavelength of visible light that produces the color you are looking at right now. So, where did it come from? Reality, edited. Welcome to Hidden Logic. Today, we are exploring the color light cannot make, and why that reveals something strange about every color you have ever seen. A rainbow is not a list of names. It is a physical sequence of wavelengths. Longer visible wavelengths are experienced as red. Shorter visible wavelengths are experienced as violet. Between them lies a continuous spectrum. A prism does not create those colors. It separates light according to wavelength, spreading the spectrum into a line. And that line has two ends, red at one side, violet at the other, but magenta is not between them. This is where the familiar color wheel can become misleading. On a color wheel, red and violet appear to meet. Magenta closes the gap between them, but the color wheel is not a map of light. It is a map of human perception. The physical spectrum is a line. The perceptual experience of hue behaves more like a loop. To understand why, we have to look at what the eye actually measures. Your eye is not a spectrometer. It does not identify every wavelength entering it. Instead, most human color vision begins with 3 classes of cone cells. They are usually called S, M, and L cones. The names refer to the ranges of wavelengths they respond to most strongly: short, medium, and long. These cones overlap heavily. A single wavelength usually stimulates more than one type of cone. The brain does not receive a label saying, "This photon was green," or "This one was red." It receives a pattern. How strongly did the S cones respond? How strongly did the M cones respond? How strongly did the L cones respond? Color begins with the relationship between those 3 signals. This means the visual system compresses an enormous amount of physical information into just a few biological measurements. And that compression creates possibilities that do not exist in a single wavelength. Magenta is one of them. A magenta-like signal strongly stimulates the long wavelength and short wavelength pathways, while the middle wavelength response remains relatively low. In simple terms, the visual system receives something like red and violet together, without the green response that would dominate the wavelengths between them. No single wavelength can create that pattern. A wavelength near the middle of the visible spectrum would strongly stimulate the M cones. It would look greenish, not magenta. So magenta cannot appear anywhere along the monochromatic spectrum. But 2 different parts of the spectrum can produce the required cone pattern together. That is exactly what your screen is doing. Zoom far enough into a magenta area on a typical display, and the solid color disappears. You will see separate red and blue subpixels emitting light. The green subpixels are dark or much weaker. The screen is not producing one special magenta wavelength. It is producing a mixture that causes your visual system to experience magenta. The color appears after the light reaches the eye. This does not mean magenta is fake. It means the phrase, "a color exists in light," is already too simple. Light has wavelengths and intensities. Color is the experience created when a nervous system interprets them. Even a spectral red is not a tiny red substance traveling through space. There is electromagnetic energy. There is a response in the cones. There is processing in the retina and brain. And then there is the experience you call red. Magenta is unusual because the gap is easier to notice. There is no single wavelength we can point to and call magenta. But the same separation between physics and experience exists for every color. In fact, most colors you see in daily life are not produced by one wavelength. Objects reflect complicated mixtures of light. White, pink, brown, skin tones, painted walls, and almost every natural surface produce broad combinations of wavelengths. The brain reduces those combinations to cone responses and constructs a stable color experience. Sometimes completely different mixtures of light produce the same cone responses. They look identical even though their physical spectra are different. These matches are called metamers. A color on a screen can match the color of a painted object without reproducing the same spectrum of light. The display only needs to reproduce a similar pattern in your three cone classes. This is why three-color screens work at all. They do not rebuild the full physical light from the original scene. They rebuild enough of the response your eyes would have produced. Your visual system completes